All right, so let's walk through this 7.3 warm up. And before I do, let's just recap. What do we know? Okay, so if we are going to be doing sampling distributions of means. Now, this is means, not proportions anymore. So what am I talking about? I'm talking about like if you went into Lake Ridge High School and you took a sample of size 40, and I was trying to find the average shoe size. Okay, so that's what I'm talking about. But then remember the idea of sampling distributions themselves is the distribution of all possible sample means, right? So then I get all these sample means and they just keep stacking and stacking and stacking and stacking, all possible, right? Not just 100 samples of size 40, but all possible samples, right? There's millions of these samples, and there's no way we're ever going to be able to get all these samples. So what we're going to rely on is the theory. The theory is if we are doing a sampling distribution of means, we can figure out the socks, right? So let's talk about those socks real quick, what you should have known. The shape we should have found out is going to be approximately normal. But how do we know that? Well, this is a twofold check. The first part of the check is if the population that we're getting all these samples from, if the population is approximately normal, then we're good. It's going to be approximately normal. But the second tier check, if this is not true or we don't know, what if they said the population is skewed right? Well, that's not normal. What if they said skewed left? That's not normal. What if they just didn't even tell us? Well, then we don't know if it's normal. So then we have a second one, and we call that the central limit theorem. Central limit theorem guarantees that our distribution will be approximately normal as long as the sample is greater than or equal to 30. That was the threshold that they found out when they were testing this over and over and over again. So this is going to come into play a lot unless we know this already. We don't have to go into the central limit theorem. All right, so that's going to give us the shape. But what's the center going to be? Well, the center is going to be the average of all those little averages should equal the average of the population. Well, that's going to be true if it is unbiased. So how do we check for something to be unbiased? Make sure it was a random sample, because random samples help us to do our best job to keep it unbiased. And let's talk about standard deviation. Standard deviation, if we look at the formula, it is theta of all the little samples, so the standard deviation of all the little samples, is equal to the standard deviation of the population divided by the square root of n. Well, that is only true if, number one, the data is independent. But remember, if it's independent, we're good to go. But what if it's not? What if we are sampling from a population and we don't let the people go back into the population because I don't want to sample them again? Well, let's go to the second tier. We call that the 10% rule. That's where we just make sure that the population is at least 10 times the sample size, if not bigger, right? So that's the 10% rule that we can check. And again, that is because we are violating, if we violate independence, it's okay as long as you don't violate it too badly. Only 10% of the population is as big as you can go before that starts to get messed up, right? Okay, let's do this now. Let's walk through this. Please take time to do this on your own. And if you haven't yet, pause it, do it, come back to it, right? That would be the best bet to do. All right, let's go. Number one, find the shape. I think that it's going to be approximately normal. But let's check it, right? Here's the check. Why would we check? So a soft drink bottler claims that on average, cans of soda, 12-ounce cans of soda. On average, cans contain 12 ounces of soda. Suppose the true distribution of soda is normally distributed with a mean 12 ounces, standard deviation of 0.6. 16 cans, there's a sample size, 16 cans, are randomly selected and their volumes are measured. Well, here's the deal. Right, if we're thinking about approximately normal, is the population approximately normal? Well, that's going to be one check. If not, let's head to the central limit theorem of n is greater than or equal to 30. Well, I'll tell you right now, the sample is not 30 or greater, so the central limit theorem is not even going to kick in here yet. But the true distribution is normally distributed. So check. I'm just going to write the word normally distributed. Okay, normally distributed. There we go. There's my check. I am good to go there. All right, number 2, let's try to find the mean. The mean, we think that the mean of all these should be the mean of the population. So here it is. The mean says it should be 12 ounces. So let's just call it 12 ounces. But let's check that. All right, how do we do a check on this? We are looking for the words random. Oh, there it is. Randomly selected. Randomly selected. Okay, check. That's going to be good. So we know that that mean's going to hold up and it should be unbiased. And let's try the standard deviation. It says that it should be the standard deviation, 0.16, divided by the square root of 16. Right, so that's going to be a calculator function. So I'm going to go 0.16 divided by 4, that's the square root of 16, and I get 0.04 ounces. But we have to check, right? This is going to just get in the habit of checking. Does it say that they're independent? No. So if it doesn't say that they're independent, then we're going to have to rely on the 10% rule, because we're pulling cans of soda off of the line, but we're not going to put them back in the line of sodas. So therefore, we are going to say, is our population, how many is there in our population? I don't know, but so we're going to say the words like all cans of soda. We're going to do all cans of soda and make sure that's greater than or equal to 10 times my sample size. So do we believe that this soft drink bottler bottles more than 160 cans of soda? I think that's safe to assume. So I'm going to check that off. Okay, now that we're ready to go, we know that the shape is approximately normal. We know that it is centered around 12 ounces, and then it has standard deviations, right? 0.04, so we can always kind of work from there. 16 cans random selected volumes. What is the probability the volume is between 11.96 and 12.08? So let's see, 11.96 is about here, and 12.08 is probably over here somewhere. Okay, so then I would say, this is what we're looking for. How many of the cans are in this range right here? Right, there's always fluctuation in manufacturing. So what it looks like they're doing is just trying to say, how often do we get it within this range? Because this range is probably considered their acceptable range for this. So let's start out by just being in the habit of doing a z-score. So what if I did 12.08 minus 12 divided by 0.04? Right, so then I got 0.08 divided by 0.04, and it looks like we're going to go exactly 2. And the z-score on this side is going to be exactly -1. So we're going between those two. So then I'm really just going to, let's finish this thing off. The probability is, let me tell you what I did in my calculator. I went to normal CDF. I put lower bound 11.96. I put upper bound 12.08. I put 12, and then I put 0.04. Right, that's what I'm going to punch into my calculator. So go normal CDF. I'm doing that. 11.96, 12.08, 12.04. And it looks like we are going to get the value of 0.8186. So about 82% chance to get your average volume between those. So the average of 16 cans Not a single can, but if I took 10 cans off the line, there's an 82% chance that the average of those 10 cans would fall in that range. That's what we're doing for. This is 7.3 work right here. This is chapter 2 work right here. And then second semester work is going to be interpreting that value, right? So that's really what we're doing here. All right, let's do one more. See how we do on this one. Okay. A hot dog manufacturer claims its most popular brand of weenie has an average fat content of 18 grams per hot dog. Supposed standard deviation of the fat content of all hot dogs is 1 gram. An independent testing organization selects a simple random sample of 36 hot dogs and finds the average fat content is 18.4. Does the result indicate the manufacturer's claim is incorrect? So this, we don't need to worry too much about this statement right here. Does the result indicate? That's really a chapter or a semester 2 idea. But what I want to do is just find the average that we get 18.4 or greater. Like what are the chances of that happening? So let's do this. Let's go number 1. We believe that the shape should be approximately normal. But let's get a little check on this one. So the check, I'm going to see, is the population normal? Nowhere in here does it say it's normal. Nowhere in here does it say it's not normal. But we have a problem because it's hard for me to say approximately normal unless I have a check. But here's what I got. 36 hot dogs. Guess what? N is greater than or equal to 30. That is true. Check. Therefore, the central limit theorem guarantees it. And we do always want to write CLT when we're talking about that. So get in that habit of doing that. All right, what is the average of all these averages here? It should be 18 grams based on the claim. Well, let's check. Let's make sure that this is going to be unbiased. They use simple random sample as their motive. So that's they're hoping to try to keep it unbiased. Number 3, we need the standard deviation of all those averages. Well, that's going to be the standard deviation of the true population divided by the square root of 36. So if we do that, 1 divided by 6, I'm just going to put that as a decimal, 0.17 grams. Let's just check that that calculation is going to hold up. So to check that calculation is going to hold up, since we're taking a bunch of hot dogs out of production, we're not going to let them go back into production. So we're going to need to check the 10% rule. So all hot dogs, testing hot dogs. Yeah, all hot dogs. I guess that's what we'll leave it like that because that's the words they use. All hot dogs, is it greater than 360? Do you think this hot dog manufacturer makes more than 360 hot dogs? I think that's safe to assume. So let's go ahead and check that off. And let's build chapter 2 work right here. 18, we know that goes that. 18.4. What is the probability that you get 36 hot dogs, average the fat content, and it's 18.4 or greater? We're going to actually just do the or greater part. So 18.4 or more extreme, right? Because that's going to help us with what we're doing. So z equals 18.4 minus 18 divided by our new standard deviation that we just calculated, 17. So 0.4 divided by 0.17. Looks like we're going to get 2.35 standard deviations away. But let's just go ahead and answer the question. Probability is, I'm going to just do this normal CDF. Normal CDF, my lower bound is 18.4. My upper bound is infinity, or I'm just going to call it 1,000. Mean is 18, and my standard deviation is 0.17. Plug that in. I get 0.009. Okay, so there is really what we want you to do here in chapter 7. But let me go ahead and answer the question to give you a little bit of a foreshadowing what is going to happen in semester 2. This says there is a 0.9% chance, 0.9% chance that we get 36 hot dogs that end up with an average of 18.4 grams or more. There's less than 1% chance that I should have gotten that, and that was the one sample I pulled off the line. Well, I think that this supplier is lying because I should not have really gotten that one sample. I was super lucky to get that sample. So therefore, I would like them to adjust their claim. I think their hot dogs actually have a content that's higher than 18 grams. It might actually be pushing 18.4. Who knows what it's actually pushing? But I just took 36 random hot dogs off the line, averaged them, and it was 18.4. And that should have happened less than 1% of the time. Either I'm super lucky and I should go play the lottery, or their claim is wrong, right? And that's what we have to assess later on in second semester.